Namaste. Now we know about the form of trees, that is the shape of trees. We also know about the taper of trees, which tells us the rate at which its diameter is reducing as the height increases. Now, if we wanted a single factor that could tell us about both the form and the taper, what would that be? Remember that the aim of forestry is to grow more and more wood, to generate more and more biomass, and to harvest more and more biomass. Not only because this biomass is going to help the society fulfill its various needs, but also because this biomass is a form of sequestered carbon, which helps in the mitigation of climate change. So, in this lecture we shall look at form factors and form quotients as a rapid way of discerning a tree's taper. So, let us come to the form factor. A form factor is the summary of a tree's shape. It summarizes the shape of a tree. Basically, it represents the ratio of the volume of a tree to the volume of a specified geometrical solid of similar height and base diameter, which is generally a cylinder. So, what do we mean by this? If we had a tree, so suppose we take this as our reference plane. Here we have a diameter of d and consider the height of the tree to be h. We are considering these branches to be growing to that height. So, if we made another solid figure that had the same diameter and we generally take it to be a cylinder. So, consider this to be a cylinder. So, this is a cylinder with the same diameter as that of the base and the same height as that of the tree. Now, if we calculated the volume of tree and divided it by the volume of cylinder, that would give us the form factor F. So, basically the form factor of a tree or stem is defined as the stem volume expressed as a proportion of the volume of a cylinder of the same height and with a diameter equal to the stem diameter at the selected reference point. Now, why do we choose a cylinder to measure this tree? Well, the answer is because it is very easy to calculate the volume of a cylinder. If we knew its diameter d and if it knew its height h, we have volume is equal to pi r square h or pi d square by 4 into h. So, we can very easily calculate the volume of the cylinder, and if we knew the form factor, we could just multiply F multiplied by volume of cylinder and it would give you the volume of the tree. But now the question is, where do we measure the diameter of the cylinder? Do we measure it at this point? Do we measure it at this point? Do we measure it at this point? Because remember that the diameter is going to go on decreasing as we move up the tree. So, which is the reference point at which we should be measuring the diameter? Similarly, what is the height of the tree? Do we suppose if we measured the diameter from at this point, do we take this height? Do we take this height? Which is the height that we should be taking? So, the references that we choose give us different form factors. Let us look at the first one, the absolute form factor. If we take the base of the tree as the reference, we get the absolute form factor. So, let us draw a tree. Now, suppose this is the ground level If we took this as the reference, we would get the absolute form factor. So, essentially here the diameter of the tree of the cylinder is the diameter that this tree has at its base, and the height is the total height of the tree. If we did that, and if we calculated the form factor by dividing the stem volume by the cylinder volume, we would get the absolute form factor. Now, this form factor is intuitive to use, however, it is hardly used in practice. Why? Because at this reference, we might be having some small shrubs around here, which would make it extremely difficult to get this diameter correctly. At the same time, in the case of forestry, we have a convention of measuring the height at a height known as we measure diameter at a height known as the breast height. So, what does breast height mean? Suppose we have an individual who stands like this. So, the height of his or her chest is called the breast height. In our country, breast height is usually taken to be as 1.37 meters. In the case of certain European countries, it is taken as 1.3 meters. So, this is a standard, and we regularly measure a tree's diameter at this height. So, now if we took this diameter, which is called the diameter at breast height, if we took this as the reference and we took the complete height of the tree and made a cylinder. So, this would be the cylinder. So, if we took this cylinder and if we calculated the form factor, this would give us the false or artificial or breast height form factor. So, it is equal to the volume of the tree divided by volume of cylinder with diameter at breast height at its diameter and the height of the tree as the height of the cylinder. We also have another form factor called the true or the normal form factor. Here we take a reference, say 10% of height. So, in the case of the breast height or the artificial form factor, we were taking 1.37 as an arbitrarily chosen. So, this is arbitrarily chosen height, which makes it artificial. But suppose we did not choose this height, suppose we took something as say 10% of height. So, let us take another tree. So, suppose this height is h, and suppose we said that we are only going to measure its diameter at a point that has a height h prime which is 10% of h. So, we are not fixing this height arbitrarily to be any fixed figure for all the trees, but in the case of this tree we will take a height that is 0.1 h, and here we are going to measure the diameter, and then we are going to construct a cylinder. So, how does it make it more normal? Because suppose we had a smaller tree at the same base, because this height is lesser, the reference point will not be the same as that of the larger tree, but we would take another reference that is 0.1 of h double prime, that is this height. So, essentially in the case of a true or normal form factor, the height that we take is not fixed, but the percentage that this height has in reference to the total height of the tree is taken as constant. So, this makes this procedure much less arbitrary as in the case of the breast height form factor. However, in this case we first need to measure the height of the tree. From that we need to determine what is 0.1 h, and then we need to take this reference and then we need to do the measurements. So, this makes it a bit more intricate as compared to the breast height form factor. So, it makes it also a bit more demanding than the breast height form factor. So, the breast height form factor is the most commonly deployed form factor in the case of forestry. So, what is the usage of this form factor? How does it help? Well, it is easy to measure the breast basal area from diameter at breast height, and it is easy to measure the height of a tree. So, if we consider the tree, if you stood at this point, easy to take its diameter at this point. We could use a tape or we could use calipers. Now, calipers are very similar to the vernier calipers that you have used in your school days. So, basically you have a scale and you have a fixed arm and a moving arm, and you have a scale. So, this reading would give you the diameter at breast height. So, it is very easy to discern the dBH of this tree. Similarly, it is easy to measure the height of the tree. So, we could use our trigonometric principles or we could use a number of other equipments to measure the height of the tree. So, we can very easily get the volume of the cylinder. So, the volume of the cylinder would be pi into dBH by 2 whole square multiplied by the height of the tree. So, we can very easily get dBH, we can very easily get the height, and so we can very easily get the volume of the cylinder. Now, if the form factor for a particular site, species and age is known, we can very rapidly get the volume of any tree from the volume of this cylinder. Now, it is difficult to measure the diameters at this point, this point, this point, and so on to get the actual volume of the tree. So, volume of the tree is difficult to measure, but if we had the form factor, we could very easily multiply form factor by the volume of the cylinder to get the volume of the tree without the need to measure its form or its taper. Thus, form factor acts as a rationalizing factor in the calculation of tree volume. So, let us now look at some specific breast height form factors for some different shapes. Consider the shape of a cylinder. So, here we have a cylinder. What would be its breast height form factor? So, suppose you stood here and took its diameter at the breast height. So, its dBH will be equal to d, where d is this diameter. Now, the height of the cylinder that you would be plotting is the same as the height of your original cylinder. So, your form factor would be volume of the cylinder divided by volume of cylinder, which will be equal to 1. So, the breast height form factor in the case of a cylinder is 1. Now, let us calculate the breast height form factor in the case of a cone. So, let us first calculate the absolute form factor. So, in the case of an absolute form factor, you would have the diameter of the cylinder, which would be the same as d. The height of the cylinder is the same as the height of this cone, which is h. Now, what is your form factor? Form factor is the volume of the cone divided by the volume of the cylinder with the same dia and the same height. Now, volume of a cone is 1 by 3 pi r square h. The volume of the cylinder is pi r square h. Now, r is your d by 2, so we replace it by d by 2 here as well. Now, h and h cancel out, d by 2 square cancel out, pi and pi cancels out. So, the form factor becomes 1 by 3. Now, if we calculated the form factor for a conoid, or say for a frustum of a cone, suppose your cone did not go till the end, but it went till here. Suppose you wanted to calculate the form factor for this figure. So, here you will have the volume of the cylinder would be the volume of this cylinder with the same height as that of the conoid. What would be the form factor? Now, it turns out that in this case the form factor would be in the range of 0.3 to 0.45. So, now looking at the slide, we can see the specific form factors, the specific breast height form factors for a number of different figures. In the case of a cylinder, it is 1. In the case of a neiloid, it goes from 0.2 to 0.3. We can take a middle value of 0.25. In the case of a conoid, it goes from 0.3 to 0.45. We can take 0.33 as a representative figure. In the case of a quadratic paraboloid, it goes from 0.45 to 0.55 with 0.5 as a reference. And in the case of a cubic paraboloid, it goes from 0.55 to 0.65. So, we can take 0.6 as a reference value. So, after the form factor, we now come to form quotients. A form quotient is defined as a ratio of diameter at two different places on the tree. So, it is a single number that depicts the rate of decrease in the stem diameter or a ratio of diameter at two different places on the tree. So, now let us draw a tree. So, now suppose we took two references and we said that we are going to measure the diameter at this height h1 and we are going to measure the diameter at this height h2. So, here we have d1 and here we have d2. Now, if we chose these as references and if we defined that d2 upon d1 is a ratio, so we can define this ratio as the form quotient. Now, as in the case of a form factor, here too the choice of the reference points gives us different form quotients. So, the first one is called the false form quotient. A false form quotient takes the diameter at 50% height as the numerator and the diameter at the breast height to be the denominator. So, in the case of a false form quotient, if we took a tree, we need to take two diameters. Now, one diameter is when you stand here and measure it at the breast height, which is at 1.37 meters. So, that is your dBH. Then the next thing that you do is to measure the height of the tree, which is if it comes to h, then you take a point that is at 50% of the height. So, this is at 0.5 h and you measure the diameter here. So, we write it as d 0.5 h. So, diameter at 0.5 height. So, your false form quotient which is written as Q 0.5H is equal to D 0.5H divided by the dBH. So, this is the false form quotient. We also define true form quotients. Now, a true form quotient is it takes diameter at 50% height in the numerator and the diameter at 10% height in the denominator. So, in the previous case we had arbitrarily taken this dBH, which is arbitrary, in the denominator. Now, if we did not choose this figure 1.37 meters and if we took it as the fraction of the tree height, so in the case of a true form quotient, we take a tree and so the steps of calculating a true form quotient would be, the first step is to calculate the height of the tree, then to take two locations, one is at 0.5 h and the second location which is at 0.1 h. Now, we measure the diameters at these two locations. So, this is D 0.1 h and this is D 0.5 h. Now, the true form quotient which is represented by eta. So, eta 0.5 h is equal to the diameter at half of the height divided by the diameter at 10% of the height. So, this is the true form quotient. The Mitscherlich form quotient is a term that is used for merchantable trees. It takes the diameter at 5 meters height in the numerator and the diameter at the breast height in the denominator. So, how do we find the Mitscherlich form quotient? You take a tree, then in this case you do not need to find out the height of the tree. So, this has pure economic values. So, first of all you stand in front of the tree and you take its diameter at the breast height. So, this is 1.37 meters and this is the dBH. Then you take another diameter that is at 5 meters. So, this is a D5. Now, the Mitscherlich form quotient is given by D5 divided by the dBH. So, why is this important? Because in this case we do not need to measure the height of the tree. So, it simplifies the calculations a lot. We also have another form quotient called the Hohenhall's form quotient. Now, in the case of a Hohenhall's form quotient, it takes the diameter at breast height in the numerator and the diameter at 10% of the height in the denominator. So, how do you calculate the Hohenhall's form quotient? You take this tree, first of all you go and stand in front of the tree and measure its dBH at 1.37 meters and then you measure the height of the tree. Then you take a location that is at 0.1 of the height and you measure this diameter which is D 0.1 h. So, the Hohenhall's form quotient is given by the dBH divided by D 0.1 h. So, the diameter at 10% of the height. Now, remember that in the previous form quotients we had taken dBH in the denominator. So, this is the only form quotient that is taking dBH in the numerator, and this form quotient is highly affected by age. So, suppose the height of the tree is 13.7 meters. What would be the Hohenhall's form quotient in this case? So, h is equal to 13.7 meters. So, h 0.1 h is equal to 1.37 meters, which is equal to dBH. So, the Hohen's form quotient would be dBH divided by d 0.1 h is equal to dBH divided by dBH is equal to 1. So, if the height of the tree is 1.37 meters, the Hohen's form quotient is 1. Now, what happens if the height of the tree is greater than 1.37 meters? So, if h is greater than 13.7 meters, 0.1 h is greater than 1.37 meters is greater than dBH. So, what would be d 0.1 h? Now, because 0.1 h is greater than dBH, so this line would go above the dBH. So, in this case we will be because this tree is tapering towards the top, we will be having d 0.1 h is less than the dBH. So, what will happen to the Hohen's form quotient? It is dBH divided by d 0.1 h. Now, because d 0.1 h is less than dBH, so this figure would be greater than 1. So, if tree height is greater than 10 times dBH, then Hohen's form factor is greater than 1. If tree height is equal to dBH, Hohen's form factor is equal to 1, and if tree height is less than this is 10 times is less than 10 times dBH, we will have QH is less than 1. Now, the height of a tree goes on increasing with its age. So, basically whether QH is greater than 1, equal to 1 or less than 1, and what would be its exact value would be dependent on its age. So, this is one form quotient that is highly dependent on the age of the tree. So, now let us do one problem. Let us calculate the form factors and form quotients for a tree. For a pinus petula tree with dBH is equal to 45.6 centimeters, height is equal to 27.4 meters, and the total stem volume, that is the volume of the tree, is equal to 1.782 cubic meters. The bole diameters at various heights are given on the next slide, and we need to find out the true form quotient, the false form quotient, the true form factor and the false form factor. So, here are the heights and diameters at those heights. So, as we can see, as the height goes on increasing, the diameter goes on decreasing, telling us that this is a tapering tree. And we need to calculate the form factors and the form quotients. So, how do we do that? We are given the diameters and heights at various locations. Now, the way of solving this problem is to first of all plot the diameter height curve. So, as we can see in this figure, this is similar to what we did in the very beginning. We take dia on the y axis and the height on the x axis, and we plot these various values that are given to us. We would get a curve that goes something like this. Again, this would be the conical portion, we would be having a parabolic section, and we would be having a niloid section. But once we have plotted this curve, we can find out the diameter at any height and the height corresponding to any diameter. So, once we have plotted this curve, next we will need to find out the interpolated diameters at various heights. So, what are the pertinent heights here? We need d 0.1 h, d 0.5 h. Now, because the height is known, so d 0.1 h will be equal to d at 2.74 meters, and this would be equal to d at 13.7 meters. From the curve, we can calculate the interpolated value. This comes to be 40.2 centimeters and this comes to be 30.7 centimeters. Now, we are given that the dBH is 45.6 centimeters. So, what is the false form quotient? The false form quotient is given by Q 0.5 h is equal to d 0.5 h divided by the dBH. Now, d 0.5 h we have found from here. So, this goes at 30.7 divided by 45.6 is equal to 0.673. Now, what is the true form quotient? True form quotient as given by eta 0.5 h is equal to d 0.5 h divided by d 0.1 h, which comes to 30.7 divided by 40.2 is equal to 0.76. Next, we need to calculate the volumes of the cylinders. So, now the volume of a cylinder with a reference diameter of 45.6 centimeters, which is the dBH, and a height of 27.4 centimeters, it comes to be pi by 4 d square h is equal to pi by 4 into 0.456 square, because we need to convert 45.6 centimeters into meters, into 27.4 is equal to 4.47 cubic meters. And the volume of a cylinder with a reference diameter of 40.2 centimeters, that is d 0.1 h, and the height of 27.4 meters. So, essentially we want this diameter and this height. So, if we calculated the volume of the cylinder, it would be pi by 4 d square h is equal to pi by 4. We took this diameter 30 point d 0.1 h, that is 40.2 centimeters. So, that becomes 0.402 meters square into the height of the tree, that is 27.4 meters. 27.4, it comes to 3.48 cubic meters. So, this is the volume of a cylinder with dBH and height, and this is the volume of a cylinder with d 0.1 h and height. Now, we are given in the problem that the volume of the tree is 1.782 cubic meters. Volume of the tree is 1.782 cubic meters. Now, we need to find out the true form factor. Now, true form factor is given by the volume of the tree divided by the volume of the cylinder with d 0.1 h and height, which becomes 1.782 divided by 3.48 cubic meters is equal to 0.512, and the false form factor is equal to the volume of the tree divided by the volume of the cylinder with dBH and height. So, this becomes 1.782 divided by 4.47 is equal to 0.399. So, these are the true and the false form factors. So, as we can see in this example, it is very easy to calculate the form factors and the form quotients. Thank you for your attention. Jai Hind.